On August 29, 1940, a military carrier qualification flight ended in an emergency water landing. The aircraft was a Grumman F3F-2 biplane, Bureau number 0976, nicknamed the Flying Barrel. First Lieutenant Robert A. Gowler, assigned to Marine Fighting Squadron 2 at Naval Air Station San Diego, was at the controls. During the critical phase of his approach, the single radial engine stopped producing thrust. A catastrophic loss of power at low altitude left the pilot with no viable operational alternatives. A successful ditching in a compact fighter requires precise airspeed control just above the stall limit. The pilot executed this maneuver, successfully ditching the aircraft into the Pacific Ocean and safely escaping the cockpit before the airframe sank. The destroyer USS Chandler maneuvered to the crash site and rescued him from the water. While the pilot survived, the airframe was lost to the ocean floor. For decades, no recovery followed the ditching. Only much later, after the aircraft was found again, did the submerged fighter become a chance to test the old explanation against physical evidence. The primary operational constraint of that later retrieval would be locating the airframe, rigging it securely, and extracting enough surviving structure without destroying the evidence still trapped inside its systems. Structural survival was not guaranteed. When an aircraft sinks during a mishap, investigators face a severe evidentiary limit. Without the physical hardware, investigators had to lean on witness statements, pilot testimony, maintenance records, and the surviving documentary record, including First Lieutenant Gowler's report detailing his final cockpit actions before the engine quit. Yet the investigation board still could not physically verify his account. They could not run functional tests on the aircraft systems or inspect the engine core for catastrophic damage. In military aviation, a sudden loss of thrust on approach can result from pilot error, fuel mismanagement, or a mechanical system failure. The aircraft itself holds the only definitive proof. Every valve, lever, and internal fuel line acts as a mechanical memory of the exact state of the aircraft at the moment of impact. Because the Grumman fighter descended beyond the recovery limits of the era, that mechanical memory was locked away. The official record accepted the ditching, but the precise physical mechanism that forced the aircraft out of the sky remained unverified. Carrier qualification flights demand absolute precision. The pilot must manage airspeed, altitude, and aircraft configuration within strict margins. Any deviation or sudden equipment failure turns that narrow margin into an immediate fleet safety problem. The Grumman F3F-2 was a heavy fighter, requiring specific pilot inputs during the final approach phase. Operating out of Naval Air Station San Diego, Marine Fighting Squadron 2 utilized these aircraft to train aviators for the unforgiving environment of carrier decks. When a failure occurs in this environment, understanding the root cause is critical for the safety of the entire fleet. If a component is inherently flawed, other aircraft in the squadron are at risk of suffering the exact same failure. If the failure resulted from a procedural mistake, training protocols must be adjusted immediately. The loss of Bureau number 0976 created an immediate gap in this feedback loop, leaving the fleet without the hardware needed to convert the mishap into a confirmed corrective action. Decades passed, and the ditched aircraft transitioned from an active mishap investigation to a historical cold case. The Pacific Ocean acted as an impenetrable barrier, protecting the wreck from salvage but subjecting it to continuous deep water conditions. If the wreck could be located and recovered, its internal components could still be disassembled against the 1940 record. However, delayed recovery would shift the case from a standard accident inquiry into a salvage problem, where engineering access had to serve the evidence rather than destroy it. What hidden fault could starve the engine while usable reserve fuel remained on board? The final resting geometry of an aircraft on the sea floor dictates the limits of any future investigation. An airframe resting flat on its lower fuselage offers stable and conventional lifting points. Conversely, an airframe positioned vertically entirely alters the structural math. The Grumman fighter settled at an extreme depth of 1,800 feet. The deep ocean environment at this level creates severe handling constraints. Beyond the depth limits of ambient pressure diving, direct human intervention is physically impossible. Any site inspection, documentation, or rigging must be executed remotely, heavily governed by the exact orientation of the wreckage. The ocean bottom at this location was soft enough to swallow the forward end of the wreck. The aircraft did not settle flat onto this surface. It came to rest nose first in the sediment, leaving the tail section pointing steeply toward the surface. This near vertical orientation meant the heaviest structural component, the radial engine, was completely buried in the mud. An investigative team cannot examine a buried engine, and they cannot attach standard recovery slings to wings suspended in the water column without risking a structural tear. To understand how the aircraft achieved this specific resting state, investigators analyzed the final moments of the flight. The primary operational constraint during a carrier approach is continuous thrust. The aircraft was positioned approximately 300 yards from the USS Saratoga, leaving the drag-intensive biplane with only seconds of usable glide energy. The pilot initiated a standard procedural decision to prepare for landing. He reached into the cockpit matrix and switched the manual fuel selector valve from the primary tank to the reserve tank. The objective was to ensure a guaranteed, uninterrupted fuel supply for the demanding deck landing. Only the later recovery would show what this routine action had exposed: a fault in the fuel selector system. A fuel selector valve routes aviation fuel from isolated tanks toward the engine-driven pump and carburetor. If the selector closes one path but does not properly open the reserve path, the engine may sputter as the available fuel flow collapses. In Gaylor's case, the engine did not die in a single clean instant. It sputtered, he worked the hand wobble pump, and then the power loss became unrecoverable at low altitude. That collapse turned the approach into a steep, unpowered descent geometry. Without engine power, the pilot faced a strict aerodynamic trade-off. He had to maintain airspeed to prevent an uncontrollable stall, which meant trading his minimal remaining altitude for forward momentum. The only available consequence was an unpowered ditching into the ocean. After the ditching, the aircraft appears to have survived largely intact, but seawater rapidly overcame the remaining buoyancy. The aircraft slipped beneath the surface, beginning a long descent to the deep ocean floor. During the descent, the engine mass controlled the pitch attitude while hydrodynamic forces held the lighter tail high. Through 1,800 feet of seawater, the flooded airframe continued nose first, converting the impact geometry into a buried nose salvage problem. With the engine buried, the primary load-bearing bulkheads designed to support the engine and absorb landing shocks were unavailable as recovery hard points. The visible upper wings and tail surfaces remained in the water column, but they were built for aerodynamic loads, not the suspended weight of a flooded metal fuselage during a deep water vertical lift. The physical state of the wreckage was permanently locked by this burial sequence. The same depth that protected key fuel system evidence from wave action also turned that evidence into a difficult extraction target. Any attempt to extract the physical proof would require pulling a buried engine block straight out of cohesive mud without tearing the fragile tail section away. How could an investigative team safely approach an airframe anchored vertically in deep mud? The next failure was spatial, not mechanical. In June 1988, the United States Navy Deep Submergence Vehicle designated DSV Turtle was operating off the California coast. The operational objective of this mission was an acoustic and visual search for a recently downed helicopter. During this designated sweep, the vehicle sensors detected an unrelated anomaly. Visual inspection confirmed the largely intact airframe of a Grumman biplane with damage visible but the fuselage still recognizable. The survey crew recorded the precise geographic coordinates, establishing a high-confidence geospatial baseline for the site. At this stage, the discovery was purely observational. The crew lacked the equipment, authorization, and structural engineering data to attempt an immediate lift. They logged the position and departed, leaving the site unbothered. Those 1988 coordinates made recovery technically possible. However, the site was left completely unmonitored for nearly 2 years between the initial discovery and the scheduled recovery mission. The unmonitored site remained exposed to industrial maritime activity. Commercial fishing fleets operating deep water bottom trawls use heavy steel doors dragged directly across the seafloor to keep their nets wide open. This industrial process creates a severe hazard for vertical wreck sites. When these massive nets encounter an elevated obstacle like an aircraft tail section projecting upward into the water column, the net does not cleanly pass over the obstruction. Instead, it securely snags on the structural framework. The immense forward momentum of the surface vessel transfers directly down the tow cables, applying extreme lateral force to the fragile airframe. This benthic drag forcefully uproots the buried forward section and pulls the heavy mass across the ocean floor. The dragging continues until the netting either tears under the extreme tension or abruptly slips free, depositing the target in a completely new and undocumented location. In early April 1990, the Fleet Ocean tug USNS Narragansett searched the coordinates recorded by DSV Turtle. The recovery team deployed sensors to reacquire the target, expecting a localized acoustic return. The sea floor at the designated datum was entirely empty. Because deep water remotely operated vehicles possess incredibly narrow visual fields, missing a target by even a fraction of a mile is equivalent to losing the sight entirely. The engineering team aboard the tug chose not to abandon the recovery effort. Instead, they designed a secondary grid on the assumption of benthic displacement and expanded the search outward from the original dead center coordinate. On April 4, 1990, the remote-operated vehicle successfully intersected the visual signature of the missing aircraft. The physical evidence led the team to conclude that a commercial trawler had dragged the airframe approximately 800 feet from its originally discovered position, forcing a full recalculation of the site geometry. The violent drag across the ocean floor did more than alter the immediate terrain. By the time the recovery team found it again, the aircraft was no longer the largely intact target seen in 1988. The engine had been torn away, the starboard wings were severed, and the tail area had suffered heavy damage. The relocation confirmed that the remaining target was still viable for salvage, but the lost baseline and damaged structure forced one question: what hard point could still take the load of an extraction? Every deep water extraction forces a structural trade-off between ideal rigging geometry and the physical limits of remotely operated access. Here, the original buried nose problem had become a damaged airframe rigging problem. An ideal salvage plan would have used a balanced multi-point cradle to distribute the weight of a flooded fuselage and transition it safely through the water column. However, the damage and the limited reach of the remotely operated vehicle left the team without enough accessible structure for that kind of arrangement. The engineering team aboard the USNS Narragansett was forced to identify an alternative attachment strategy. They could not route cables around the external fuselage without crushing the internal framework. Visual inspection via the remotely operated vehicle confirmed that the port main landing gear strut remained exposed above the mudline. The landing gear of a heavy biplane fighter is constructed from a strengthened tubular framework, strictly engineered to absorb massive downward impact forces during carrier deck landings. By selecting the single strut as the lift point, the recovery team had to completely reverse the intended mechanical load path of the component. Instead of compressing the shock strut downward to absorb energy, the salvage operation would require the strut to pull upward against the full tension weight of the aircraft. This single-point lift limit creates a severe engineering hazard. If the internal attachment brackets shear under the extreme tension, the aircraft will plunge back to the ocean floor, permanently destroying the structural evidence it contains. Committing to this exact attachment point shifted the constraint from structural engineering to remote robotic manipulation. Securing a heavy-duty lift line at extreme depth without the use of ambient pressure, divers requires flawless execution. A remotely operated vehicle relies on hydraulic manipulator arms that completely lack tactile feedback. The operators aboard the surface vessel must judge depth, clearance, and line tension entirely through a two-dimensional camera feed, operating under the delay of tethered communication. The strap had to pass around the landing gear leg without snagging surrounding aluminum skin or non-structural fairing, because any false contact could slice through the metal as soon as tension came on. The remotely operated vehicle required 4 hours of continuous, methodical maneuvering to properly position, thread, and lock the single lift line around the left main landing gear leg. The surface operators had to constantly manage the vehicle tether to prevent fouling against the elevated tail section while compensating for deep ocean currents that continuously pushed the vehicle away from the target structure. Once the line was positively secured, the operational baseline was permanently set. The connection was robust, but inherently asymmetric, and any lift would twist the damaged structure while concentrating abnormal tension on the port landing gear. The remote rigging was complete. The lift would now test whether the landing gear's attachment brackets could carry a flooded aircraft in tension. The physical extraction of a submerged airframe from extreme depth dictated a strict operational time window. Initiating a continuous mechanical pull from the sea floor introduces extreme dynamic loading hazards. Aboard the Fleet Ocean tug, the crane operator faced the immediate local constraint of ship heave. Even a calm ocean generates vertical surface swells. As the surface vessel rides over these waves, the stern rises and falls. If the winch is simply locked, this vertical displacement transfers directly down the steel cable. A rising ship abruptly yanks the cable upward, while a falling ship introduces sudden slack, followed instantly by a severe snapping force. To protect the asymmetric single-point attachment, the crane operator adjusted winch speed against the ship's heave, while the deck crew began a slow pull, increasing line tension in small increments and watching the port gear for failure. The force gauge registered the load as the ship pulled upward. This was the failure mode the team had been working to avoid. The material held. The landing gear structural leg successfully bore the tension weight of the remaining flooded aircraft, and the damaged biplane began its long ascent through the water column. During the vertical transit, the operational focus shifted to managing hydrodynamic drag. Although the aircraft was heavy, the displacement of water provided continuous buoyant support, effectively reducing the overall suspended weight. However, pulling a solid shape upward through fluid creates downward drag forces. If the winch pulls too quickly, the water resistance can strip away weakened aerodynamic fairings or buckle the fuselage stringers. The engineering decision was to maintain an intentionally slow, deliberate ascent rate, prioritizing structural survival over operational speed. The flooded aircraft ascended steadily, hanging awkwardly from its offset rigging point, while ocean currents introduced a slow torsional rotation to the suspended load. The most dangerous phase of any maritime salvage is the transition through the air and sea interface. As the uppermost sections of the aircraft breached the surface, ocean buoyancy fell away, and every gallon trapped inside the fuselage, wings, and engine cowling became dead weight. Lifting a fully flooded aircraft completely into the air will snap lifting cables or tear the airframe apart under its own immense mass. The crane operator paused the hoist with the aircraft suspended half in and half out of the ocean. This pause allowed the thousands of pounds of trapped seawater to slowly drain back into the ocean through open inspection hatches, degraded skin panels, and the cockpit enclosure. After the internal water volume dropped far enough, the crew began the final hoist, reported at 9 o'clock at night on April 5, 1990. Operating entirely under artificial ship floodlights, the deck crew faced the final hazard of pendular motion. A suspended load swinging freely above a steel deck risks severe impact damage if it strikes the ship's superstructure. Using taglines and careful deck handling, the crew arrested the twisting motion of the airframe. They guided the dripping wreckage over the stern and carefully lowered it onto a prepared deck cradle. The heavy tension was finally released from the landing gear strut. The extraction phase was officially complete, successfully moving the fragile artifact from the sea floor to a stable industrial platform. The structural envelope of the aircraft survived the transit intact, but transitioning from an oxygen-starved environment to the open air rapidly accelerates corrosion. Once exposed to the air, what evidence actually survived a half-century in deep salt water? The recovered airframe narrowed the question from whether anything survived to what kind of evidence had survived and in what condition. The thin aluminum exterior had suffered most severely, and that material reality dictated the restoration sequence. When an aircraft is extracted from the ocean floor and moved into a dry facility, the forensic investigation splits into two parallel tracks. One track stabilized the surviving structure, the other targeted the mechanical components responsible for the loss of the aircraft. For the team handling the Grumman fighter, the corrosion risk now had a specific chemistry. The deep ocean environment is highly destructive to thin aircraft alloys. When dissimilar metals like dense steel engine mounts and thin-gauge aluminum skin panels are submerged together in an electrically conductive fluid like saltwater, a continuous battery effect is created. This process triggers severe galvanic corrosion, heavily attacking the less noble aluminum components. Furthermore, chloride ions present in seawater aggressively attack protective oxide layers on aluminum, driving deep pitting and structural exfoliation from the inside out. Over 50 years of continuous immersion, this chemical attack dissolved the structural integrity of the external skin. Upon inspection, the engineers found that the severely oxidized exterior panels could not be stabilized, patched, reattached, or trusted to hold fasteners. The team made the procedural decision to scrap the compromised material, which ultimately required a 60% replacement of the original aluminum sheet metal skin. While replacing such a large volume of the aircraft reduces its percentage of original material, it was the only viable engineering trade-off to permanently stabilize the surviving tubular framework and prepare the airframe for long-term museum display. While the external skin acted as a sacrificial layer against the ocean environment, the heavy internal mechanics of the fuel system were heavily shielded. This preservation allowed investigators to shift their focus to the primary objective of the recovery, which was isolating the exact cause of the 1940 engine failure. The task now was to isolate the component in the operational chain without destroying its mechanical context. The technical team focused on the fuel selector system and the fuel still associated with the reserve tank. As they examined the valve assembly and related fuel lines, they made a critical discovery. Usable fuel had remained in the reserve side of the system, while the faulty selector valve had prevented that supply from reaching the engine. This evidence supported the central point of Galaire's account without proving every small cockpit detail. This fuel evidence provided the strongest physical support for Galaire's account while still leaving minor cockpit details beyond direct proof. Galaire's procedural claim now had a physical anchor. The result was the finding that mattered. The engine had been starved while usable fuel remained on board, effectively closing the central accusation against the pilot and replacing a 50-year-old suspicion with strong mechanical support. Following a meticulous 3.5-year restoration, the rebuilt aircraft was transferred to the National Naval Aviation Museum for permanent preservation. It stands as a fully stabilized historical artifact, but more importantly, it serves as the physical resolution to a strictly defined engineering cold case.